So I said, good morning, Yusuf. Sorry, my microphone was muted. So, all right, before we actually start the course, do you have any questions about the course in general, homework, stuff like that? I mean, we could solve homework in class or whatever. Even though I think it's more important to just get on with the course. All right, let's get on with the course. Or do you have any comments? I mean, they don't have to be questions. They can also be comments. Okay, so besides the three most important classes of first-order equations solvable by integration, by direct integration, which are called integrable by quadratures that we have seen so far, there are many more. I'd say at least 10, but probably more than that. And out of these, as I promised in this course, we are going to study 5 in total. I mean, I can tell you about more of those, but probably outside the class. There's no need to spend time on that in class. And so the 5 that we are solving in class are separable equations. We have been there, done that. Linear equations. So we have spent some time on linear equations in general, but so far we have only really solved first-order linear equations. And we'll come back to linear equations in general in the third half of the course. By that I mean the third part of the course. And we have also gone over exact equations, which are also pretty important, and which include separable equations as a special case. Did I actually present to you those slides? So separable equations are a special case of exact equations. Well, if I didn't, then you can remind me next time or whatever, and we can go over that. So now we are on to the 4th and 5th classes of equations, namely Bernoulli type equations and homogeneous type equations. So unlike the first 3, these 2 have an extra twist in their solution. Namely, it requires essentially twice as much work as the previous 3 kinds. So for the 3 previous kinds, all that we had to do is integrate and some clever algebraic manipulations. For these 2 kinds, in addition to that, we have to make a substitution. So, which is not necessarily an algebraic manipulation, it's more like an analytic manipulation to the equation. So we have to make substitutions in these equations. And for each of them, there exists one specific substitution that always works. So the solution is algorithmic. And if you don't know the correct substitution to use, then it's vanishingly unlikely that you'll be able to figure it out by yourselves. I mean, I know this because I was taught these substitutions, and I have no idea whether I would have been able to find them out by myself or not. So there's one more distinction to make here between homogeneous type equations, which we are studying now, and homogeneous linear equations, which I mentioned, I think, over the past 2 classes. So on Monday and on Friday, and before that. So homogeneous linear equations are those linear equations for which the source term is 0. Homogeneous type equations may or may not be linear, so it's not impossible for them to be linear, but they are not distinguished by what I just said. So it's not about the source term or whatever. So there's a special type of functions which are called homogeneous functions, and that's part of the definition of homogeneous type equations. And probably we're going to get to that in the next course, because this course is about Bernoulli type equations. But I just thought I would tell you. So, and these homogeneous type equations in general are very, very nonlinear. And linear equations in general can have any order. So they can, and for all of them, there exist some common features and common solution methods. But homogeneous type equations that we'll be studying next class are always first order. So there are lots of differences. The only similarity is in the name. So the name includes the same word, homogeneous, homoousios, if you know Greek. So now let's talk about Bernoulli equations. So an ordinary differential equation is of Bernoulli type if, as written here, it can be written in the form dy over dx plus p of x times y is equal to q of x times y to the n. So you can take this as the definition because it is the actual definition. P of x and q of x are functions of x. Okay, so P of x and Q of x are coefficients in the equation. If n is not equal to 0 or 1, the equation is nonlinear. If n is equal to 0 or if n is equal to 1, then the equation is actually linear, and it can be solved by the method of the integrating factor that I have spoken about before. And if n is not 0 or 1, then exactly as I said a couple of moments ago, then the solution requires one extra step, namely we should make the substitution. And again, this is not an algebraic transformation. This is an analytic transformation. So we need to make the substitution. U of x is equal to y to the power y minus n, where n here is the power of n in the right-hand side of this equation. And this substitution is guaranteed by a proof to transform this equation into a linear first-order equation. If n is equal to 1, the equation is already linear first-order, so there's no need to make the substitution. Actually, if n is equal to 1, can you tell me what other type this equation might have? Just have a good look. If n there, the power of y is 1. So what? Separable, right? That's right. So if the power n there is 1, then we can factor y, and we get dy over dx is equal to q of x minus p of x times y. And the equation is also separable, but it is also linear. And it is also of Bernoulli type. But if n is equal to 0 or n is equal to 1, then we should not use the substitution that's written here. So in that case, we should use the other methods that we have already learned about separable equations or about linear equations. All right, so what else can we tell here? This equation is certainly first order. It may or may not be linear. It may or may not be autonomous. So if you want, you can look at it for a second, and you can think about when it's going to be autonomous and when it's not. So when it's autonomous, I think it will also be separable. So whatever. Now, this is the proof, which is written on the slide, that the substitution always works. So we make the substitution, u of x is equal to y of x to the power 1 minus n. So then y is equal to u of x to the power 1 minus n. So I don't need to write the parenthesis x all the time for you to know that this is a function of x, right? And the same applies in general when it's a function of some other variable, like t. So The equation is the one written up here. I just copied it from the previous slide. And so we use this substitution. So if u is equal to y to some power, then y is equal to u to 1 over that power. Like if u is equal to y squared, then y is equal to u to the power 1/2. But this is not completely true, as you can imagine, for even powers. So even powers are a bit more special in that regard. So if u is equal to y squared, then y is equal to plus or minus square root of u. And the same is true for all even powers. For odd powers, so if 1 minus n is odd, then we don't need the plus minus. When 1 minus n, in particular when n is not an integer, so n can be either positive or negative, or it could be a real number, or it could be a complex number, whatever. So rules differ according to each power. But I suppose that you know enough algebra to figure what happens in each case. If not, we can talk about it. So dy over dx, the derivative of y with respect to x, we just take the derivative of this function u as a function, u to the power 1 minus n as a function of x, and we use the chain rule. So the derivative of u to the power 1 minus n as a function of u is 1 over 1 minus n times u to the power 1 over 1 minus n minus 1. And then if, since we don't want to take the derivative as a function of u, but we want to take the derivative as a function of x, then dy over dx is equal to dy over du times du over dx. So again, this is not just algebra. I mean, it's not just a pair of fractions and you cancel du with du from each side. This is an analytic rule. It's an analytic theorem. So then the dy over du is this first part here, and then it's times du over dx by the chain rule. Is it clear up to this point? If you have any questions, go ahead and ask. Or comments. You can state them if you have them. Okay, no questions, no comments. Okay. So then we make this substitution according to the chain rule as computed here into the equation. And here I wrote it 1 over 1 minus n times u to the power 1 over 1 minus n minus 1 times u prime. And then it's plus p of x times u to the power 1 over 1 minus n. So why is that? It's because this was y here in the equation, and I replaced it by u to the power 1 over 1 minus n. So this is equal to q of x times y to the n, which is u to the power 1 minus n, quantity to the power n. So we have a bunch of different powers of u here in the equation, some of which need not be integers, some of which need not be real numbers, so some of which can be complex powers. And then 1 over 1 minus n times this thing. So we multiply the whole equation by u to the power minus 1 over 1 minus n plus 1. So why do we do that? Because it turns out that this is going to cancel both the first power of u and the third power of u. So again, following some algebraic manipulations, we see that u to the power 1 over 1 minus n minus 1 times this quantity gives 1, because u to some power times u to the minus some power equals 1. And u to the power 1 over 1 minus n times u to the power minus 1 over 1 minus n plus 1. So this is the middle power, the second power here. So they don't completely cancel, but they give us something equally desirable. Namely, they give us just u by itself. So u to the power 1 over u 1 minus n cancels u to the power minus 1 over 1 minus n, and we're just left with u to the power 1, which is u. And for the third power, so u to the power 1 over 1 minus n times u to the power minus 1 over 1 minus n plus 1. So they completely cancel again because so u to the power a raised to the power b again is u to the power a times b. So this first factor here on the left-hand side is just u to the power n over 1 minus n. So it cancels the other one. So why does it cancel? Again, here's the explicit computation. N over 1 minus n minus 1 over n minus n equals n minus 1 over 1 minus n, which is minus 1. Minus 1 plus 1 is 0, and u to the 0 is 1. Any question up to here? So in any case, you can refer back to the slides later. I think the proof is written explicitly enough. And so what do we get after we perform all these operations? We get 1 over 1 minus n. So as I said, the power of u here cancels, plus p of x times u. So the second power of u does not cancel. Instead, it becomes u is equal to q of x. So the third power of u again cancels. All right, so this is definitely a linear equation, but it is not written in the standard form. Does anybody know what is missing? What extra step we need to do in order to bring it to the standard form? Okay, if nobody knows, let it be so. So then we take, so this is the last result on the last page. And so the last missing step is that we want to have the derivative of u in the equation, which is written here. So we want to have it by itself. So we want to remove the 1 over 1 minus n factor. So in order to do that, we multiply the whole equation by 1 minus n. So this is one of the reasons why using this method in the case when n is equal to 1 wouldn't make sense, because we would be multiplying the equation by 0, which is a perfectly valid operation, but it does not establish equivalence. So if we multiply the equation by 0 on both sides, we would just get that 0 is equal to 0, which we already knew. So we would be losing information. I mean, the original equation tells us much more than the fact that 0 is equal to 0, which, by the way, we already knew. So we shouldn't follow this scheme, this algorithm, in the case when n is equal to 1. So what about when n is equal to 0? Well, I'll leave you to think about what happens when n is equal to 0. So after we multiply by 1 minus n, we get u prime plus 1 minus n times p of x times u is equal to 1 minus n times q of x. So this is certainly a linear equation. Now it is also written in the standard form, and you can solve it using the method of the integrating factor that we have spoken about earlier. And after we do this, this is still not the final step. Up to this point, we have only computed u. But what we want to find is the solution of the original equation. Namely, we want to get y. So as you see written here, y is u to the power 1 over 1 minus n. And again, this is not exactly true. It depends on what sort of power 1 minus n and 1 over 1 minus n are. But I think you're smart enough to figure this out for yourselves. But if not, I mean, or even if you are, you're definitely free to ask me. So one more pretty important observation. If we make the substitution in the case when n is a number that's strictly bigger than 1. I don't know why I wrote n strictly bigger than 0 there, but who cares? So if n is a number that's strictly bigger than 1 here, then when we make the substitution, u of x is equal to y to a negative power, then we are implicitly dividing by a power of y. So that's only allowed when y is non-zero. And then in addition to everything that we have discussed so far, we also need to consider the case when y is constantly 0. So actually, maybe even when n is not a number strictly bigger than 1, we need to, so this only applies to real numbers. When n is a complex power, then we can always make the substitution. I mean, when it's a complex number which is not a real number. And so when n is a real number bigger than 1, then we cannot divide by some power of y without first checking whether y is 0 or not. And then it turns out, so when n, so actually probably this is why I wrote n bigger than 0 there. So when n is bigger than 0, then the equation is guaranteed to admit the solution y is constantly 0. So I guess something different happens at the threshold when n is bigger than 0 and when n is bigger than 1. But in any case, you need to check separately for this solution. I mean, if you want your solution to be complete. So let's check in general. If we plug in y is constantly 0 in the equation, then p of x times y is 0. Y prime is also 0 because the derivative of a constant function is 0. And q of x times y of n, well, there it depends. So again, if n is a positive power, then, or maybe also if n is a real number, is a complex number, which is not a real number, then y to the n is guaranteed to be 0 as well. If n is 0, then I guess the question whether 0 to the 0, I'd say that 0 to the 0 is 1 as well. But whatever, that's a more complicated question. And if n is a negative real number, then when y is constantly 0, y to the n is undefined because you cannot raise 0 to negative powers. So now let's consider an example. I mean, I could also include this stuff in the lecture notes, but I think having it included in the course recording is fine enough. So I'll upload the course recording a bit later. And so now let's look at a concrete example. So let's consider the equation y prime plus 2y is equal to e to the x times y squared. This is clearly a Bernoulli type equation because we have the power y squared here on the right hand side. So n is equal to 2 according to the algorithm that to the definition that I have just stated. And this is the value of n that we'll use in the algorithm to solve the equation. So the coefficient of y, which I call p of x, so it's pretty good to be consistent with notations. So once I've called it p of x, I should stick to p of x when talking about this equation. And this coefficient, I called it q of x, and I'm going to stick to calling it q of x as long as we talk about this equation. So consistency is pretty good. It's not mandatory, but it's pretty good. So in this equation, again, p is 2 and q is e to the x. And n, the number here, so the power of y is 2. Sometimes instead of n, I call it d. But I think in this course, I'll stick to calling, or sometimes I call it alpha, whatever. But in this course, I think I'll stick to calling it n. So then we should make the substitution. U is equal to y to the power 1 minus n. Here n is 2, So this is y to the minus 1, which is 1 over y. And again, this is the observation I made just a couple of moments ago. Namely, by doing this, we are missing the solution y is equal to 0. And here I'm claiming that it's a valid solution, but you need to check. And I already did the checking in general on the previous slide, whatever. So, so this is also separately a valid solution that we need to include at the end, and which is not captured after we make the substitution u is equal to 1 over y. So, well, so let's continue after making the substitution, just keeping in mind that there's a separate valid extra solution. So after I make the substitution, if u is 1 over y, y is 1 over u, and y prime is minus u prime over u squared. Right. So now I made the substitutions into the equation itself, and we get that minus u prime over u squared plus 2 times 1 over u, which is 2 over u, is equal to e to the x over u squared. So y squared is 1 over u squared. And then we multiply the whole equation by u squared. So again, this is only an implication here. It's not an equivalence. Why is it? Can anybody tell me why it's not an equivalence? Why I used a monodirectional arrow instead of a bidirectional arrow here? So it's because in theory, u itself could be 0. And then when we multiply the equation by u squared, it's not an equivalence that goes both ways. So we should always be able to multiply by u squared, but we should not always be able to divide again by u squared in order to get back to the original equation, because u could be 0. However, actually this consideration does not apply here, because we defined u to be 1 over y, and 1 over y can never be 0. So whatever, this is just an aside. So after we multiply the equation by u squared, we get minus u prime plus 2u is equal to e to the x. And this is a linear equation, but it is not in standard form. So I'm saying this the second time. This minus in front of u prime makes the equation not be in standard form. And namely, so it's still a linear first order equation, but this is not the form you should use to solve it. Because if you do, you're almost guaranteed to make mistakes. So we multiply the whole equation by minus 1, and we get u prime minus 2u is equal to minus e to the x. So now the equation is in standard form, because it is of the form u prime plus some coefficient times u is equal to the source term. So can anybody here in the audience tell me what's the coefficient of u and what's the source term in this equation? Nobody can tell me? Let it be so. So it is important that the equation is in standard form, because otherwise, again, you are very liable to use the method of the integrating factor incorrectly. So this is the third time I've said it. Okay, so now let's look at this equation, and let me remind you the method of the integrating factor. I mean, who knows whether you can remember it from one week to the next. So y prime minus 2u is equal to minus e to the x. The integrating factor here is mu of x, which is e raised to the antiderivative of the coefficient of u. So the coefficient of u is minus 2. So this is e raised to the antiderivative of minus 2, which is minus 2x. And here, again, as I've mentioned numerous times, we don't need to use a constant. So we don't need to write minus 2x plus c. Minus 2x here is good enough. So we multiply the whole equation by the integrating factor, e to the minus 2x. And we get e to the minus 2x times u prime minus 2 e to the minus 2x times u is equal to minus e to the minus 2x. And then again by the product rule, which, like two other things that I've mentioned in this course, is an analytic manipulation. It's not an algebraic manipulation. So d over dx of e to the minus 2x times u, so the whole left-hand side combines by the product rule or by the Leibniz rule, which are the same thing, into the derivative of e to the minus 2x times u. So the derivative of a product is given by the Leibniz rule, or as it is sometimes called the product rule. So this derivative is minus e to the minus x. So why is it only e to the minus x here? Because, actually, why is it e to the minus x here? Because we took e to the x and we multiplied it by e to the minus 2x, and we got e to the minus x. Okay, hopefully this is clear enough. So now let's get on with this on the next page. So this is the last formula that was written on the previous page. And now integrating both sides. So the integral or the antiderivative of the derivative is the function itself, plus a constant, if we want to. And so here we got rid of the derivative, and we are just left with e to the minus 2x times u. Again, possibly plus a constant. And then this is equal to the antiderivative of minus e to the minus x. And the antiderivative of minus e to the minus x is e to the minus x plus another constant. And then, as I have told you repeatedly, we only need to actually write the difference of the two constants, which may or may not be the same. I mean the two constants. And it's good to write this difference on the right-hand side. So here, I have skipped calling these constants whatever C1, C2, C3. I just show their difference and called it C. So again, this integration is not an algebraic manipulation, it's an analytic manipulation. So these occur at several steps in the proof. So now we multiply both sides by e to the 2x in order to get rid of the factor of e to the minus 2x in front of u. And we get u of x is equal to e to the x plus a constant times e to the 2x. So e to the minus x here times e to the 2x turns out to be e to the x. So this is not yet the final step, because we are not only interested in finding out what u is, this is just an intermediate step. The final step is finding out the solution of the original equation, which is y. So y was u to the minus 1. I mean, this is how we define u as y to the minus 1, and y is also u to the minus 1. So then we get that y is 1 over this. So it's 1 over e to the x plus c to the 2x. And for any constant c in R, this is a solution. So this is almost the general solution. And then there's that special solution, y of x is constantly 0. So now this whole expression here is the general solution of the equation. Any question up to here? So hopefully this example is clear enough. We have touched most of the special things and particular cases that, that can happen. But now let's move on to the next example. Well, okay, so before the next example, I see I have a slide here about what we still have plenty of time. Yeah, we have around 20 more minutes. So the next slide here, which shows you how to solve an initial value problem for this type of equation. So on the previous slide, we found the general solution. Now here we'll find the particular solution that corresponds to the equation together with initial conditions. And the initial condition here, so we only need one of them, is because this equation is first order, is y of 0 is equal to 2. So now, since we have already computed the general solution, let's use it. And the first thing that we need to do is we need to decide in which of these two branches we are. Are we in the left branch or are we in the right branch? And since y of 0 is equal to 2, we are most certainly not in the right branch because the right branch is just the constant function 0. So this means we must be in the left branch. And then in the left branch, so the solution is of the form 1 over e to the x plus a constant times e to the 2x. And in order to find the particular solution to this problem, we need to compute the value of the constant c that corresponds to this initial condition. So we plug in x equals 0 and y is equal to 2, as you can see here. So y becomes 2, 1 is still itself, 1 over e to the 0, so e to the x becomes e to the 0, plus constant times e to the power 2 times x, which becomes 2 times 0. And of course, e to the 0 is 1, e to the 2 times 0 is equal to e to the 0, which is again 1. So we get that 2 is equal to 1 over 1 plus c, which is the same as saying that 1 plus c is equal to 1/2. So c is equal to minus 1/2. So the solution of this initial value problem is 1 over e to the x plus minus 1/2 times e to the power 2x, which is the same as e to the x minus e to the 2x over 2. And we can, of course, simplify or whatever, rewrite the solution a bit further, but this is the particular solution of this equation. And now one more observation here. This solution is not defined on the whole real axis. It's defined only on a half line. So certainly, as you can check by plugging in x is equal to 0 here, the solution is, this function is well defined as 0. But you cannot extend it to infinity on both sides. So you can certainly extend it to minus infinity. So as x approaches minus infinity, e to the x approaches 1, and you have 1 over 1 minus 1/2, which is 2. But as you're going forward, and whatever, it's well defined all the way from minus infinity to 0, as you can check. And then from to the right of 0, it's not defined for the entire positive half axis. It's only defined up to a point. And that's pretty easy to compute the value of x at which the solution has a vertical asymptote. It becomes infinite in finite time. So, no, actually, we could do this computation here. Why not? I haven't used the board for this class yet. So let's use it. So this is so stupid. So stupid. Hi, Allison. So we have so we had y of x is equal to 1 over e to the x minus 1/2 e to the 2x, or something like that. Now we're trying to decide the question, when is the denominator of this fraction equal to 0? So that's the point at which this function will have a vertical asymptote. So, well, let's solve it. E to the x minus e to minus 1/2. Actually, let's skip this step. E to the x is equal to 1/2 e to the 2x. Is equivalent to two is equal to e to the power x. So I canceled one of the e to the x's, and I'm just left with 1. And I multiply the equation by 2. So now 2 is on the left-hand side, and the 1/2 canceled. So which is equivalent to, yeah, actually now it's no longer really equivalent, but whatever, I'll write it. So I think it's only equivalent for real numbers. So it's equivalent to x being natural log of 2. So actually, if we are trying to go forward in time, then the solution will have a vertical asymptote at the point natural log of 2. So actually, the domain of this function is the maximal domain of existence. So I mean, it can have a variety of domains, but the maximal domain over which it makes sense within the real line is from -infinity to natural log of 2. So let's write this properly. And yes, I know that it can also be defined for all values which are strictly bigger than natural log of 2. But when solving ordinary differential equations, we want the domain of the solution to be an interval. So there's no way for us when solving an ordinary differential equation to just jump over the point where the solution blows up. I mean, it has to be done continuously. Starting from the initial point, we go continuously backwards as far as possible, and we go continuously forward as far as we're allowed. But we cannot jump over points where the equation has a vertical asymptote, or in other words, where it blows up. So here, the maximal domain of existence of the solution is the open interval from -infinity to natural log of 2. Go ahead, you want to ask a question? So, okay, so let's assume that you cannot figure that out by yourself. And then, if that's the case, then I multiplied both sides of the equation by 2, e to the minus x. So multiplying both sides of the equation by 2 gives you 2e to the x is equal to e to the 2x. And then multiplying both sides of the equation by e to the minus x gives you 2 is equal to e to the x. But let's do this step by step again, assuming that you, no, but that's fine. I mean, I don't mind. We have lots and lots of time. Yeah, so let's write this part completely properly. So, I mean, I think it's fine to skip steps, and it's fine to write things completely properly, but let's do this computation and write it completely properly for once. So e to the x is equal to 1/2 e to the 2x. Okay, so first, so this is actually, as far as I can tell, actually, this is the proper notation for when you multiply an equation by a constant. Namely, you draw a red bar to the right-hand side of the equation, and you write here dot whatever you're multiplying it by. So in our case, you're multiplying the equation by 2. So then this implies that 2e to the x is equal to, so does anybody here know how much 2 times 1/2 is? Nobody? 1? Okay, well, that's better. So, and we don't need to write the 1 because 1 times something is that something. So it's equal to e to the 2x. And now we multiply the equation by e to the minus x. And this implies that 2 times, so this is completely unnecessary, but I'm just doing it so that I show you what the most formal possible way of writing this could be. So 2 e to the x times e to the minus x is equal to e to the 2x times e to the minus x. And then, okay, I mean, this is more than enough formalism for me. E to the x times e to the minus x gives 1, and e to the 2x times e to the minus x here gives e to the x. 2 times 1 is 1. E to the x is itself. And this implies that 2 is equal to e to the x. So this is a much more formal way of writing this computation than I have done before. So as you can see, I skipped a lot of steps. But I mean, you are free to either write all the steps explicitly, or in the interest of time to skip a number of steps if you're sure that you can do this and have your computations correct. And even if they are correct or not, it's always good to check afterwards. Okay. So it's always good to check afterwards, even if you're 100% sure that your computations are correct, because it's always possible to make algebra mistakes. Okay. So any question up to this point? Do you want to do some more steps here very explicitly? Okay, so now let's go back to the slides, whatever. So whatever. All right, so this is where we were in the slides. And now we've moved on to the next example. Why does it say my screen share is paused? Well, let's say resume share, whatever. Okay, now I'm screen sharing. So y prime plus y over x is equal to x squared y cubed. This is the next example. Let's see, do we have time for it today? Yeah, I think we have. We still have 4 minutes, we can do it. But this time I'll go faster. So y prime plus y over x is equal to x squared y cubed. The coefficient of y is p, which is 1 over x. The coefficient of y cubed is q, which is x squared. The power of y in this equation other than 1 is 3, which is n. And then we make the substitution. U is y to the power 1 minus 3, according to the algorithm, which is y to the minus 1/2. So the major difference between this example and the previous example is that if y is equal to minus 1/2, this does not give us a specific value of y. When solving this for y, we get that y is equal to plus or minus 1 over square root of u. However, u has to be positive, because u to the minus 1/2 is the same as 1 over u squared, and the square of any real number is non-negative. And 1 over u can never be 0, so y to the minus 1 squared has to be strictly positive. So u has to be strictly positive for this to work. And in addition to that, as I've said before, you also need to consider the special solution y is constantly 0. So, okay, so now let's go with the substitution. We can use either y is equal to u to the minus 1/2 or y is equal to minus u to the minus 1/2. You can actually check both cases, but the second case is completely analogous to the first case. So, and both of these cases are not keeping track of the special solution y is constantly 0. So one of these two cases traces all strictly positive solutions. The other one of these cases, namely this one, traces all strictly negative solutions. And there's a third case when the solution is constantly 0. And this is specific to this equation. So in general, things are similar, but not quite completely the same. And if y is u to the minus 1/2, we make this substitution into the equation. And we get y prime is minus 1/2 times u to the minus 3/2 times u prime. So I plug this into the equation. Minus 1/2 u to the minus 3/2 u prime plus u to the minus 1/2 over x is equal to x squared times u to the minus 3/2. So u to the minus 1/2 cubed is u to the minus 3/2. And now let's go on to the next page. We'll multiply this equation. By the way, this does not look like a linear equation, and it's actually not a linear equation because it contains so many other powers of u which are not 1, but it can be easily turned into a linear equation by multiplying both sides by u to the power 3/2. And we get this linear equation, minus 1/2 u prime plus u over x is equal to x squared. So u to the minus 3/2 cancels with u to the 3/2. U to the minus 1/2 times u to the 3/2 gives 1. And u to the minus 3/2 times u to the 3/2 equal 1 as well. So, okay, this is the equation that we get. Now we multiply both sides by minus 2, and we get u prime minus 2 over x. So this is because we multiplied by minus 2. So minus 2 times u over x is equal to minus 2 over x times u. And then looks like I forgot to write a minus sign here. So whatever, you can assume that this is minus 2x squared. And I'll correct the slides afterwards. So u prime minus 2 over x times u is equal to minus 2x squared. The integrating factor is e raised to the antiderivative of the coefficient of u, because this equation is in standard form. And then the antiderivative of minus 2 over x is minus 2 natural log of absolute value of x. So e to the minus 2 times natural log of absolute value of x is absolute value of x to the minus 2, which is equal to 1 over x squared. So whatever, I skipped a few steps here. So now we multiply the whole equation by 1 over x squared, and we get that u prime over x squared minus 2 over x cubed times u is equal to 2. And again, we can only do this. Well, so this is actually a different thing. We can only do this when x is not equal to 0. So in this equation, x is equal to 0 is also a special case that needs to be examined separately when solving initial value problems. So u prime over x squared minus 2 over x cubed is equal to u times u is equal to minus 2. And then by the product rule, both terms on the left-hand side combine and give you the derivative of u over x squared being equal to minus 2. Okay, so now we integrate both sides. We get u over x squared is equal to minus 2x plus a constant. So u is equal to minus 2x cubed plus a constant times x squared. Okay, so here's another mistake. But actually, let's try to fix this right now, at least on this slide. So this is going to be, let's see, minus, no. Okay, let's try again. Okay, so let's say this is, but I didn't want to put it there. So this is minus 2x plus a constant. So this is minus 2x cubed plus cx squared. Yeah, and that's not a 3. So let's undo this. Plus cx squared. Okay. So this is minus 2x cubed here plus cx squared. Everything raised to the power minus 1/2. And then it's plus or minus because actually u is plus or minus u to the minus 1/2. And as I have mentioned before, for this equation at least, it's either going to be always plus or always minus in a solution. So there are no particular solutions that combine both the plus and the minus because the plus branch is strictly positive, the minus branch is strictly negative, and you cannot jump from one to the other without going through 0. And the solution has to be continuous. Okay, so this is actually the general solution of this equation. And let's see, and this is the last slide for today. Sorry for going a little bit over time. Have a great morning. And I'll make these corrections actually in the slides before I post them online after the class. Thanks again.